All right, we are going to get started. So we'll start with that review of a set complement and then move forward to the last few things. Sets are what's going to be the dominant aspect of discrete that's going to be present in this class, with some sides of proof types. The actual proofs themselves probably won't be particularly important, but I will be asking people from time to time to be like, if we needed to prove this, what proof type could we use? And that will hopefully help make some of the connections between the class make more sense. So set complement. Let's start with a nice small universe so that the set complement doesn't end up being massive or infinite. So we're going to set our set universe to be the set of 1, 2, 3, 4, 5. This is everything in the entire universe. You don't exist. I don't exist. You didn't eat anything for breakfast this morning. There's no such concept as breakfast. 1, 2, 3, 4, and 5. Why am I talking about? I talk about food in every class that I teach. Why is this? There's something subliminal here. But we are in a psychology class, so we're not going to worry about it. It's not part of the universe. So let's say some set S is the set. I don't know. Someone give me 2 of these numbers. 2 and 4. 2 and 4. So the idea behind S bar, or the complement of S, is going to be, we want everything from the universe that is not in that set. So this is the universal set minus the set S, which is everything present here that is not present here. So it's just 1, 3, 5.
I guess my question is, how does that differ from the difference of a set?
Because we have this concept of a universal set.
Okay.
So we define the complement to be, rather than anything else, just a universal set, whatever that happens to be.
Okay.
Everything that could possibly be in a set that belongs to that universe is not in that set. That's a great question. And we'll see throughout this course that we'll find some interesting universes. We'll have the universe of all strings in a particular language. So we would say something like all possible English strings minus all nouns. That would be the complement of all nouns, all possible words that aren't nouns. But we don't want to include words that aren't in English or sequences of characters that aren't words in any language. We only want to include in our universal set something that makes sense, or that is everything that we could be talking about right now. And we'll get into different kinds of languages and how those can be useful in our own computation. And then eventually how we can use that to do fun things when it comes to transitioning and building compilers. Questions on this before we move on? Okay, De Morgan's laws aren't going to come up a ton, but it gives you a nice, hopefully, tie back to something you've seen before as a way of seeing this is a way of understanding a complement. Next, a subset. This will come up all of the time in this class. So we will say that a subset S sub 1 is a subset of another set S if every element of S sub 1 is also an element of S. So the subset symbol looks like this. So S sub 1 is a subset of S. That's what that tells us. So let's say that S is the set. We're going to make this even smaller now. 1, 2, 3. What are all possible subsets of S?
It's like 1, 2, 3, 1, 2, 1, 3,
Yeah.
2, 3 kind of thing.
So all subsets would include, we want to include the empty set as one of those. A set that contains nothing is always a subset of a set, including the empty set. It is a subset of itself. It can also be the set that contains 1, the set that contains 2, the set that contains 3, the set that contains 1 and 2, the set that contains 1 and 3, the set that contains 2 and 3, and itself the set that contains 1 and 2 and 3. There's some gross curly braces. Those will get better as the quarter progresses.
And those can be in any order, right? Does that matter?
So a subset would be any one of these. This is the set of subsets
Okay,
of possible subsets of this set.
but like 2, 1 would count as a subset.
Correct.
Okay.
Yeah, you're right. The order and multiplicity don't matter here. So you don't need to permute this in any way because it's embedded within that, as well as multiplicity also is. This is the same set as the set that contains 1 and 2 and 3 and 1 and 2 and 3 and 3 and 1 and 2 and 1 and 3, as long as I don't include another new element. So all possible subsets, order and multiplicity do not matter in this or in any of these. Questions on the concept of a subset? Let that up momentarily because we're going to talk about a proper subset, which means that it's a subset, but not the exact set that contains exactly the same elements. So it contains fewer elements than the original set. So a proper set, you can think of this kind of like a less than or equal to. That's at least intuitively how I like to imagine it. This is equivalent to like a less than or equal to, and this is just strictly a less than. This is a subset, meaning that it could be fewer elements or the same number of elements as long as all of those elements were present in the original set. And a proper subset must have fewer elements. You cannot have exactly the same set. A set is not a proper subset of itself. I spoiled things a little bit talking about a power set, because a power set is the set of all possible subsets. So when I drew out all of those possible subsets, that was the power set of that set. We write power sets as 2 to the power of the set. Why does that make sense? Why would we use this notation to describe this set of sets, the power set of this set? Yeah.
The number of sets are in the power set.
Yes. Why does that intuitively make sense? So we know the cardinality of this set is 3. 2 to the 3rd power is 8. If we count the number of sets that are in this set, we have 1, 2, 3, 4, 5, 6, 7, 8. That will always be the case. Why?
Because the number of combinations you can make is 2 to that power minus 1, but then we include the empty set, it gets that number.
Yep, that's one way to think about it. There are actually quite a few intuitive ways to arrive at this conclusion. And rather than draw out the mathematical proof, which is what would probably happen in a math class, I find it more memorable to think about just the logic of why is that the case. Break it down into some components and try to come up with some reasoning for why that makes sense. You'll remember a lot more in 5 years if you can tie it to something memorable. So I like to break it down into how many sets of size 0 do we have? How many sets of size 1 do we have? How many sets of size 2 do we have? So we have 1 set of size 0. We have 3 sets of size 1. We have 3 sets of size 2, and we have 1 set of size 3. Does this sequence of numbers look familiar?
I can't remember the name for it, but it's that weird triangle, right?
Yes.
Yeah.
It is a row of Pascal's triangle. If you were to do this with a set of size 2, just A and B, what would the power set of that look like? We would have the empty set, which again, we can draw as just an empty set, or we can draw it as the null symbol. Either one of those are equivalent. We would have A, the set that contains A. We would have the set that contains B. We would have the set that contains A and B. Of size 0, we have 1. Of size 1, we have 2. And of size 2, we have 1. That is the row above that row in Pascal's triangle. So this breaks down into combinatorics. This breaks down into basically the binomial theorem as to how many elements, because you're choosing of all of these elements, you're choosing one of them. You're choosing, sorry, 0 of them. You're choosing one of them, you're choosing 2 of them, or you're choosing 3 of them. So this breaks down into 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So just trying to tie some things together that you might have seen before. It's giving you other ways to think about breaking down the power set. And if we draw out Pascal's triangle and sum each row, we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Sum each one of these and you get 1, 2, 4, 8, and 16, which is, this is row 0. This is row 1, this is row 2, this is row 3, and this is row 4. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. So we get this notation out of that. Math notation becomes a lot less cryptic if you tie it to why it is. Questions about this? I love discovering these things. Whenever I discover something new like that, it just gives me a new way of seeing that. Oh, that's so cool. It's all related. Big fan. Last thing we'll need to know, I think, pretty close, a Cartesian product. If we have two sets, the Cartesian product is the set of all tuples such that the first element, first of all, do we remember what a tuple is? And the notation for a tuple? So a tuple is with parentheses rather than with curly braces. And this is an ordered pair. Think of it like coordinates in a coordinate plane. The X comes before the Y. So this is ordered. This is not the same as the tuple BA. So now we're given two sets. Let's say we have S sub 1 is the numbers, let's go with the letters first, A, B, and C. S sub 2 is the set containing some numbers, 1, 2, and 3. So the Cartesian product of S1 and S2 are going to be all tuples such that the first element of that tuple is an element of S sub 1, and the second element of that tuple is an element of set S sub 2. So what is a legal tuple from this Cartesian product? Any of them? E2. E2. That is one such one. So all of them would be, we would have A1, A2, A3, B1, 2, 3, C1, C2, and C3. I think I did that right. So this is the set of all of these tuples. So you draw a set notation around this list of tuples. The order of these tuples within this set, because it's a set, does not matter. But the order within each of these tuples now does matter because it's a tuple and not a set. And order matters in tuples. If we tried to flip this, then it would be one of the elements of the Cartesian product of the reverse of these two sets, because the order of these two sets now matters in terms of the Cartesian product. So this becomes, the notation for this is S sub 1 cross S sub 2. if you wanted to draw this in a nicer, neater form, rather than listing all of this out, you could write something that looks a little bit more mathematical. So we say S, the Cartesian product of two sets, S sub 1 and S sub 2, are all tuples x, y, such that X is a member of set 1 and Y is a member of set 2. So this is just mathematical notation, but that's exactly how you would read it. All tuples x, y, such that X comes from S1 and Y comes from S2. Or has membership. But it represents this set. Questions on the concept of a Cartesian product? Okay, the other really important topic from discrete that we're going to be drawing on fairly frequently, and this is the last thing that I'll go over for this review. I'll go over other things as we get to them, and especially in a very small class. Basically, just let me know if I'm going over something and you don't understand the notation. I will try to explain all notation that I use at this level of depth. Here's what it means. Here's an example. If I ever do not do that to a level that you are comfortable with, let me know. I'm happy to go over it. But this is the last thing I'll go over just in general. So a function is some assignment of every element in a set to an element of another set. So we're going to take every element in the leftmost set and make sure that there is an associated element in the rightmost set. Does that make sense as far as the definition of a function? I like to think of it as kind of a map. So we're going to now draw a set vertically. So here we would have S1 is A, B, C. And S2 is now, actually I should draw this down. Let's do A, B, and C. Oh, I'm gonna put those in there. S2 is 1, 2, and 3. So I like to visualize functions in this way so that now we can draw lines between these elements. So in order to be a function, every element of S sub 1 must have an associated element of S sub 2. So we could say A maps to 1, B maps to 2, and C maps to 3. If this is the case, then this is a function between S sub 1 and S sub 2. Because every element in this set has an associated element of this set. What if I do something like this, where A, B, and C all map to 1? Is this a function? According to the definition of a function? It actually is. If we have the leftmost set, every element of this set is mapped to an element of this set. If you think of something like an XY plane, this is the equivalent of something like a straight line on y equals 1. There exist plenty of values of y that don't have an associated value of x. But every possible element of x has an associated value of y, it's just that it's always 1. So this is the function y equals 1, which is a function.
If it were the other way around, would it still be correct?
It would not. So let's look at what that would look like kind of in graph form, where we have now A maps to 1, A maps to 2, and A maps to 3. What would the equivalent be drawing on an XY coordinate plane? And we're just looking at quadrant 1 here for ease of use. There are other quadrants, we're just not going to draw them.
Vertical line.
Yeah. This would be a vertical line at x equals 1. Is this a function? It's not a function because there exist values of x that don't have an associated value of y. So this would be the function x equals 1, not y equals 1, and every function has to be written as y equals something. So that's kind of an easy way to think of what is a function. There's a leftmost set and a rightmost set. This in a coordinate plane is the leftmost set. This is the rightmost set. So every element of the leftmost set must have a value of the rightmost set. Yeah,
Clarify, if we were to give in the set example there,
Yeah.
B and C a value, but A still had multiple, would that be a function?
that would not be a function. Okay, so yeah, the other rule of this is that no element of this set can have multiple values of this. Because that gives you a piecewise function potentially, and piecewise functions, you have to kind of assume what one particular value is, and that's not both, like leaps between two values of x. But we say it's undefined at exactly that value because it can't have two values. So that's a great question, and it is the other half of this definition that I did not mention. We have some additional terms here defining the domain of the function. The domain of the function is all elements of the first set. Note that because it's a set, it can be infinite. So in an xy coordinate plane, the domain is x. It's the x-axis. When we're talking about functions, they may very well be finite and just pertain to all elements of the leftmost set. In that case, the range is all of the elements of the second set. Actually, not quite true. I think that is a reasonable definition of range. So the codomain is all elements of the second set. I don't know how that snuck in there, but the range of a function is just all elements of the second set that have an associated element of the first set. You can think of this like if we're trying to draw, I don't know, the sine wave. It's a terrible sine wave, but the codomain now is the entirety of the y-axis, and the range is now all elements of the y-axis that have an associated sine value. So this would just range between -1 and 1. This is your codomain. And this is your range. And we can say the same thing with finite sets as well. So there are more elements in this set than there are elements that are mapped to in this particular function. Questions on this? All right, we'll call that good for a math review for now. We'll probably end up doing it in counts, but that's probably also good just in general. You can only take so much boring before we have to do something fun. So let's launch slide deck 2 of 23. Yes, I made 23 slide decks for this last class. Everyone's impressed. How do you go through that much content in 1 quarter? Quickly. All right, so we mentioned, yeah, question.
Just a quick thing, is the syllabus in Canvas?
It should be. It should be, if you go there, there should be a link in there that launches the PDF.
The only thing I see in there is a 212 study guide.
Did I copy the wrong course somehow into the wrong? Good to know. I'll go figure that out. That's very much the wrong thing for this class. I thought I double checked what I was doing. Obviously, I didn't do it well enough.
It's the right class this time, not yesterday.
So last class, we started talking about some terms associated with languages that we will be using in automata. The first one was an alphabet. We're going to start getting some symbols associated with some of these concepts. So we mentioned that an alphabet is just defined to be some finite, non-empty set of symbols. We're going to denote this set as capital sigma, which looks like the sum symbol that you might have seen before. Throughout this class, we will probably be reusing and redefining some math symbols that you have commonly seen before to mean something else. I apologize in advance. Math notation is confusing. Wherever needed, I will redefine something and tell you what it stands for. But throughout the entirety of this class, where you see a sigma, this is not a sum. This is defining an alphabet. A string is some finite sequence of characters. Each character is in the alphabet. In most programming languages, we put quotes around strings. Throughout the scope of this class, there are no variables, at least lowercase variables. We'll see some uppercase variables, but if they are lowercase letters, they are characters in the alphabet. So we do not need quotes to denote strings. So if the alphabet is the set AB, we can define some strings, and they're most commonly starting toward the end of the alphabet, usually with U. So we can say the string U are the sequence of characters A, B, B, A. The string V is defined to be the sequence of characters B, A, B, B, A, B, B, A, B, A, A, B, A, 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 A. In general, A, B, C, starting at the beginning of the alphabet, is going to name characters, and lowercase letters toward the end of the alphabet will denote strings. That's just something that we will frequently see throughout the course. Some things that you can do to strings in automata theory are very similar to things that you can do to strings in programming. So you can concatenate them. You can reverse them. You can denote substrings of them. You can determine the length of them. And you can determine if a string is a prefix or suffix of some other string. If we want to denote the empty string, we have a character for that, just like we have a character for the empty set. We're going to use lambda. Lambda is just the empty string. So rather than quote, quote, which is what you're used to, for denoting the empty string, since we're not using quotes, we need some symbol for this. Throughout the entire quarter, that will be lambda. Not to confuse your past linear algebra, if you want to reverse a string, we're going to use a superscript capital R. So if we have some string W, the reverse of that string is W superscript R. if you want to repeat a string some number of times, we'll call that n. Then the integer, the number of times that you're going to repeat that string, is the superscript. So w cubed is the same as www. I'll be repeating this, I'm sure, multiple times as we go through examples where this terminology is on the board. Not a problem. It'll take a while to get used to. We need to now define some more things. We have our alphabet, sigma. Sigma star is now the set of strings obtained by concatenating 0 or more symbols from that alphabet. This is called the star closure. So let's say we have some alphabet. We'll use something as reasonably simple as possible. So in this case, sigma star is the set of all possible concatenated, so it's all the strings you can make. And it's the set of all strings. So this is going to be one giant set. What is contained in this set? I like to order these as much as possible to make them make the most sense that I can. So I will generate all strings of length 0, followed by all strings of length 1, followed by all strings of length 2. Note, this is going to be an infinite set. So the star closure of this, we start with the empty string. So we're gonna put lambda in there as the empty string. What are all possible strings of length 1 in the star closure of this alphabet? We have A, we have B. All of them of length 2. We have AA, AB, BA, and BB. We can continue this process if we wanted to. We can kind of just put a ... here that shows that we could continue with all strings of length 3, all strings of length 4, all strings of length 5, all strings of length 6. So there are going to be 1 of these, 2 of these, 4 of these, probably 8 length 3, 16 length 4, 32 length 5. So you can see how this quickly explodes exponentially in terms of the number of strings of each potential length, but there's also no upper bound to the length. So this set must contain all strings of length 17,219,410,608. You would eventually get there in this infinite set. We don't have time for that. Who am I kidding? This is your one assignment for the entire quarter. List all of these elements. Once you are done, I'll pass you.
Emission minor.
I get AI to do it.
That's how you crash an AI. I'd love to do that for you. Let me start. 1, 2, 3, 4, 5, 6. This is why we will always be smarter. The positive closure is the same thing as the star closure, but we don't include the empty string. So here we're using set difference for the first time. The star closure denotes a set. The set that just contains the empty string is a set. So this is set difference, showing us that the resulting set will be the same set as the star closure, just without the empty string. So the positive closure in this case is also an infinite set. Infinity minus 1 is still infinity. here's an interesting conundrum. We've kind of talked about this. I've kind of hinted at it a little bit. So the size of the alphabet is finite. But the star closure and the positive closure are infinite sets. That's always going to be the case regardless of the size of the alphabet. Why is that?
Because there's no restrictions on how many times you can use any letter in the alphabet.
Right. So even in the worst case, the alphabet, there's one character in the alphabet. This reduces down to the set of positive integers. You would have one element that is size 1. You'd have one element that is size 2, one element that is size 3. Yeah,
Hypothetically, could you just say in the rules of formation that, strings have to be less than 5 characters and then it is fine?
you could. We'll find that that is a language. The star closure of a particular alphabet will always be infinite. But a language, and we'll get to this, is going to be some subset of some star closure of an alphabet. When we start to place those restrictions on this, we get a language. In fact, that's the very next thing we're going to say. Strictly defined subset of the star closure of an alphabet. That's a very mathematical definition, but we're just placing some restriction exactly as we just did. We can only have at most 5 characters from this alphabet in a row. Bam, we have word. Like, okay, exactly 5. Now we have word. English words of exactly 5 characters. A sentence in a language is just some string that is in that language. So let's use that example and run with it. So if we have the alphabet, just like we did before, A and B, and now we're going to say that the language, some L, is within this alphabet, all strings, we could say S such that the size of S is less than or equal to 5. So that would be the definition of some language that represents some subset of the star closure of this language. Questions on this? Just trying to start using some of the notation that we're going to be using, bringing people on board to this notation, as well as to these ideas. Because you can start to see the relevance to programming languages, right? We call them programming languages because they are a strictly defined subset of some alphabet. If the alphabet is just all possible ASCII characters, then a language is just going to be some subset of possible sequences of ASCII characters. Some of those are going to be defined to have meaning. Some of those are not. Some of those are user-defined to have meaning. When we make variables, we're defining a string to have a particular meaning within that language. Yeah.
So a sentence is only going to be one word if the alphabet doesn't include a space.
Correct. But a string could very easily be an instruction, and an instruction may have spaces in it. So that's a good, we're going to be focusing mostly on strings that don't have spaces. But if you're thinking about the application to a programming language, then you absolutely can have white space in a single string if you define a string to be an instruction. So let's start to use some of this notation that we have been deriving. And we're going to say, here is the alphabet AB, and the language is A to the N, B to the N. What did that superscript N mean again?
And
Repeating it some number of times. So what's an example of a string in this language? AB. Excellent. So let's just start making some strings. AB is a string that is in this language. What's another string in this language? AABB would be in it. This is a great example. AAB is not in this language. Why? Yeah,
I'm worried to have both characters the same amount.
yes, this n needs to be consistent. So we need to define a value for n. So this basically says some number of a's followed by exactly that same number of b's. So AABB is in the language because n equals 2. If we wanted these to be different or allow them to be different, how could we change the notation such that we would allow different numbers of a's and b's?
AN, EN.
Sure. You could change this to be an m. And now if this is a to the n, b to the m, then this still says all of the a's come before all of the b's, but we allow different numbers of a's and b's. Excellent point, excellent distinction. There's a very important string we've forgotten that's in this language. What is it? Yes, lambda. Lambda is also a string in this language. When you set n to be 0, you get the empty string. And you can see that this pattern will continue, 3 a's followed by 3 b's, 4 a's followed by 4 b's, etc. Luckily, we can't have negatives here, which is useful for our purposes. So we started to write out the star closure. As usual, when I think about the star closure, I think about all strings of length 0, all strings of length 1. So you start with lambda. There are no strings of length 1. Strings of length 2, we have AB. No strings of length 3. AABB is the only string of length 4, etc. So you can start to use that as a way of kind of expanding to make sure that you're hitting every possible string. As you do that, you usually get some sequence that you can end with an ellipse, the ... that shows that this goes on forever. And there are an infinite number of strings in this language. We already did this. We already did this. How many sentences are in that language? Infinite. Luckily, half of infinite is also infinite. Examples of sentences that use the alphabet that aren't in the language. We came up with one. AAB was an example of a string that was utilizing characters of the alphabet that was not in the language. What are some more? A, right? You think about what is the value of this? What is the value of this? They have to be the same. So this n, a to the 1 would get you the a, b to the 0 would get you no b's. Since they're not the same, it's not in the language.
ABA.
ABBA. Sure. This doesn't allow for there to be a's after the last b. No string in this language will ever have an a following a b. Can the string start with a b? Can't do that either. So lots of counterexamples of strings that utilize characters of the alphabet that aren't in the language. So we can see that the language is a strict subset or a proper subset. Both of those are interchangeable in terms of terminology of the star closure of the alphabet. Now we can start viewing languages as just sets of strings. So we can now define the union, intersection, and difference of two languages since they're just sets. We can also define the complement of a language. So we can say the complement of the language, the universal set, is now the star closure of the alphabet of that language. All strings that you can make utilizing that alphabet. Does it make sense how you could union, intersect, and differ between two languages? Does that make sense? We want some examples of that. Sure.
Might as well.
Yeah, so we have, let's start with the same alphabet between those two. We're going to just utilize A and B, so we're gonna define the alphabet. Let's say, what should L1 be? Does anyone want to define some kind of language that utilizes this alphabet? So that would be exactly one string, which we could absolutely do. Some languages may only have one string in the language.
A and then B.
A to the N, B. Love it. Okay. What's our second language?
A, B, N.
Yeah, sure. A, B to the N. So what is the union between these two languages? There's going to be two different ways that we can handle this. We can either start to list strings, eventually finding a pattern, and then leaving the ... to show that maybe this is an infinite set. Do we know that for sure? What's the size of this language? How many strings are in this language? Infinite. How many strings are in this language? Infinite. What's the union of an infinite language and an infinite language? It's gonna be some infinite language. So we know we're gonna have to, if we start exhaustively listing strings, we're going to need at least one ellipse. It can get really ugly because you start ending up with multiple dimensions that you're working on. You're like expanding infinite of this. And then you need to define it for this. So you end up with a two-dimensional infinity. You can't just start exploring one of those dimensions because that goes on forever. When are you ever going to start the second row of that? Think of like an infinite by infinite array. When are you ever going to reach the second row of that matrix? You never will. You're going to need to use something intelligent that we will actually discuss later in this class for how to navigate that. So you could also find some way of specifying this in terms of set notation. What's up, Fatima? So we're going to define this union as L1 union L1. Does anyone have any idea of how they would want to write this out?
A to the N, B to the N.
Is that always going to be the case? That's a good idea. It's a good place to start. Is AAAB in the union of these languages?
Yes.
Yes, because it's a member of L1. Remember that a union is a member of one, a member of the other, or a member of both.
Can you just do A to the N, and then I go B to the M?
A to the N, B to the N, where N is greater than or equal to 1.
Not quite. It's a good guess. We need to be able to specify any number of A's followed by any number of B's, really, because the union of these is going to be here, where we have some number of A's and some number of. What makes this a little bit tricky is this has to have a B and this has to have an A. Is lambda in this union? Is the empty string here? No. So we need either A followed by some number of B's, or we need some number of A's followed by a B. If we were going to write this out in terms of exhaustively, we would need to, say B, AB, AAB, AAAB, ... So continue this process forever. And now you have to start with the other one, where you have A, AB, this is ABB. So now you have multiple ellipses in your infinite. Yeah,
Got it this time. A to the N, B to the M, where N or M is greater than or equal to 1, but
Yes.
not exclusive for.
yep. Yep, there you go. So we have A to the M, B to the N, such that now we need a restriction on N or M. So M or, let's say M is greater than or equal to 1, or N is greater than or equal to 1. Perfect.
Wouldn't AABB be valid with that definition? They're both greater than or equal.
Yeah, and then I guess we would need to say M is not equal to N.
Well, then AABB would work. Maybe you need M equals 1 or N equals 1, maybe.
Yeah, you're right. You're absolutely right. One of them needs to be 1. M equals 1 or N equals 1. That's better. Much better. I like it. This is the kind of thinking and the kind of problem solving that you'll be doing a lot in this class. So if this is intriguing to you, where you are saying, here's a puzzle, how can I represent this puzzle? You're gonna be doing that a lot. Luckily, it's usually going to be more visual or problem solving, but it will feel a lot like a puzzle very frequently. At least that's my goal with the design of the class. So we are unfortunately out of time. Hopefully this has been reasonably interesting. And we will come back and learn a lot more about this, and we'll actually start learning about our first automaton type. And I guess we do meet tomorrow, so we'll talk about that tomorrow.
We get to watch you.
Sorry?
We get to watch you.
We do not, unfortunately. We'll get to watch a couple of other fun things. I have one video planned for the entire quarter, but it's from, does anyone follow Veritasium on YouTube? It's from one of his, what was the video? It's like it's on the limitations of math. Because eventually we're going to be talking about that in here. What is the limit of computability? So what can math do and what can't math do? And how relevant is that to the design of our programs and languages, programming languages in general? So we'll figure that out much later in the quarter, but.
Does that go to like time complexity and that type of stuff, or is that even like before that?
I'm not going to go too deep into it because it's kind of an algorithms topic, but it is relevant in terms of, is there something where time complexity doesn't even matter? It's just, it's so not computable that in infinite time, it won't finish.
Okay, cool, right on.
Yeah,
Thank you.
yeah, thank you.